Hi everyone, I'm Kevin, and today I'll be walking you through the role and benefits of the ZTF file within the Oasys LS-DYNA environment. It is a key component that enhances our processing capabilities. Before we get started, I'd like to briefly introduce what we'll be covering in this tutorial. We'll begin by exploring the purpose of the ZTF files and the key information they hold. From there, we'll move on to the practical application, where I will show you 3 straightforward methods for generating these files automatically within the Oasys suite. And to bring this all together, we'll look at 2 demonstrations. We'll see the difference the ZTF file makes when processing models with features like cross-sections, spotwelds, and composites. To begin, let's address the fundamental question: why do we need ZTF files? Standard LS-DYNA result files, like the PTF and DFlip files, are highly optimized for storing time history data, things like displacements, stresses, and velocities. However, they don't capture all the supplementary details from the original keyword input DAG. This means that useful information, such as the include file structure and the precise location of cross-sections, isn't normally written out. To bridge this gap and provide a more complete picture for post-processing, ZTF files were developed. They act as a supplementary database which enriches the main result files with its essential static information. Furthermore, its small size allows a much faster loading compared to reading the entire keyword file. So what exactly is stored in these ZTF files? Their main role is to provide the static geometric data that complements the main time history result files. Files like the DFlip or PTF, LS-DA, and ASCII group files store the time history output of a simulation, but they don't contain the model's underlying structure. The ZTF file fills the gap. It contains a wealth of data to provide this context, including model details on beam sections, applied loads, nodal constraints, as well as part and section data. They also contain specific data on spot welds and composite material layouts, essentially acting as a detailed reference guide to your model. One of the standout features of the ZTF file is how seamlessly it integrates into the Oasys LS-DYNA workflow. These files are automatically generated when you submit a job through Oasys Shell. This means that, for the most part, you don't need to take any extra steps to create them. Then, when it comes to processing in Oasys DFlip or THIS, the software automatically searches for the corresponding ZTF file and reads that along with the main result data. This integration ensures that all the rich model data is readily available, providing a far more intuitive and efficient post-processing experience. Now, I'm going to show you how the ZTF files are generated in Oasys Shell and Primer. The most common and automated way to do this is when you submit your job using Oasys Shell. When you are ready to submit your LS-DYNA run, open the submission panel in Shell. From there, navigate to the Inputs and Outputs tab. Here, you will find an option called Primer Static Database File. You need to ensure that this option is checked. It should be on by default, but this is where you can manage it. When this option is enabled, Shell will automatically generate the ZTF file for you right after your LS-DYNA job is finished. It is a set it and forget it approach. And just like with other settings, you can save this configuration to your preferences file, so the option will always be checked for you in any future job you submit. While using Shell is the most automated approach, there are also times when you might need to create or update a ZTF file manually. For example, if you change the include file structure but did not touch any other keywords, but you don't want to rerun the simulation, just to update the model in DFlip. You can quickly generate an updated ZTF file in Oasys Primer. For that, we'll now turn to Oasys Primer, where you have a couple of options for doing this. The first way to do this in Primer is when you are writing out your main keyword file. When you are ready to save, bring up the option panel. In this panel, you'll see a setting labeled ZTF output. Simply make sure this box is ticked. This tells Primer to automatically write the ZTF file at the same time as your keyword file. Just like in Oasys Shell, If you want this to be your standard practice, you can save it as default. Just click Save Settings to OA Prep file, and the next time you open Primer, this option will already be checked for you. You can also customize what goes into the ZTF. By expanding the ZTF options, you can choose to exclude certain modules. You can also select the output style. For most situations, the default fast full output is the best choice, so I will select that and click Apply. The command window confirms that our ZTF file has been written. We can also check this in our File Explorer. As you can see, the ZTF file is right there, next to the main keyword file. Finally, there is another way to do this within Primer, which is especially useful if you only need to generate the ZTF file without rewriting the entire input deck. For this, simply navigate to the Utilities panel and select Write ZTF and Group Files. This opens a dedicated window where you can specify the location and adjust the output options for the file. Once you are ready, just click Apply to generate it. To demonstrate the practical benefits of the ZTF file, I'll be using two different models. First, we'll look at this body-in-white front section of a car, and afterwards, we'll examine a racing chair made of composite layers. We'll start with the body-in-white model. This model has been defined with several cross-sections at the front, where a block is set up to crush against the rail. It also includes numerous spot weld elements connecting different panels. So now, when the model is loaded into this report without the ZTF file, we're still able to process the data as normal. We can animate the crush event and plot results. Note that this is what a normal LS-DYNA model will look like without a ZTF file. The core data is there, but we are missing some visual information. For example, we're not able to see the exact locations of the cross-section profiles. Furthermore, the spot welds are just shown as standard solid elements, making them hard to distinguish or isolate from the surrounding structure. Now, if we load the LS-DYNA results and the ZTF file together into this report, the difference is clear. We can now see the location of the cross-section profiles drawn directly onto the geometry, and the spot weld elements are now visualized as separate entities. Here they are drawn as a sphere. This improves the usability of the model. Because this report now understands what these entities are, we can easily customize them. Under the display options, we can change the style and appearance of both cross-sections and the spot welds. A useful tip is that you can press the keyboard shortcut O to quickly switch to this panel. You can also toggle their visibility by going to Display, then Entities, and deciding whether the spot welds or cross-sections are displayed or not. This allows you to isolate the spot weld elements easily and visualize the cross-section profiles clearly within the geometry. This useful information can further be translated into t-hits. If we open t-hits and link it with our d3 section, we can now select entities for plotting just by clicking on them. For example, if we want to plot the force in x direction of this cross-section in red, we can click the Pick Visible button here. Move the mouse over to the cross-section in the d3 window and click on it. Hit Apply, and in this way, we can easily plot the force of that section. This seamless interaction is only possible because the ZTF file provides the necessary context. So as you see, the ZTF file adds a huge amount of value for models with features like cross-sections and spot welds. Now let's look at our second model to see how the ZTF file helps in a completely different context. This racing chair is made up of several composite layers and is being subject to acceleration to simulate a shaker table test. Importantly, this model is organized into three important include files: one for the chair itself, one for the connections, and one for the mounting bracket. First, let's load the results into this report without the ZTF file. If we look at the selection tool, there is no option to select parts based on the include file. We can only interact with individual parts, which is inefficient for complex assemblies. When we plot the composite stress, we see only generic layer numbers, layer 1, layer 2, and layer 3. We have no way to identify specific name piles because this report has no context from the original model. Now, let's see what happens when we bring the ZTF file into the picture. In the selection panel, a new include option is now available. This allows us to quickly isolate the entire sections of the model, which is a highly effective way to manage complex assemblies. When we return to the contour plot option, there appears a new button called Piles. We can now select a specific pile, such as front skin layer 5, and see its stress contour directly. This level of clarity and control is only possible because the ZTF file provides this report without essential model context. So, as we have seen through these examples, the ZTF file is much more than just an extra file. It is what translates your raw LS-DYNA output into a fully interactive and understandable engineering model within the Oasys suite. It unlocks functionalities that makes your post-processing faster, easier, and much more insightful. For more information, please visit our webpage. And if you have any questions, don't hesitate to talk to our support team. Thank you for watching.